Welcome back to ECE 442-542. Homework number 6 is due today. Exam number 3 is the next time you come to class, which is Wednesday, and because of that, we have our review session being held right after this particular class period. And if you're following along on D2L, you may have noticed that we're up to lecture 6.2. Today's lecture is 6.3. I've provided an extra lecture, lecture 6.4, anticipating us not getting that far in today's class. But if we do, maybe I can remove it. But that's already posted on D2L as lecture 6.4. And again, even though it's talking about PI controller, we're doing it in a way to hopefully help you review for the material that will be on exam number 3. That's the idea. And it's basically, how do you utilize these ideas or these concepts to create a controller design process? And we'll hopefully make that a little bit more clear today as we walk through. First, we'll step through the process for exam number 3, which isn't any different other than you get one more sheet of notes. So now you have 3 sheets of notes plus your Laplace or your Z transform table. And then we'll get into proportional and integral control with the root locus, which means that we'll review our proportional control. We'll introduce a PI controller and see what kind of terms that produces or gives us. Then we will summarize some of the 3 root locus rules that we've already covered. We're going to have a 4th rule and a 5th rule, but that will be for the final exam in terms of material. And then we will go through some examples with proportional and integral control and maybe get into more root locus rules, but I think that's after exam number 3. The process, as I said, I'm not going to spend much time on it. It's consistent with the previous processes of earlier exams, other than now you have 3 sheets of notes. Pardon? No talking. That's right. If you have a question, you raise your hand and I'll come find you, hopefully. You may have to, well, I don't know sign language, so maybe you'll have to talk to me once I get close to you in your chair on the exam day. Here's proportional control, the P control, the P part of a PID controller. And now we've isolated the gain K from our plant G of Z. And again, we can always find this closed loop transfer function. That's our cheer. That's Kg over 1 plus Kg in this case, where C of Z is equal to the K. And we're interested in the closed loop dynamics. And the closed loop dynamics will be visible to us if we move K from 0 to infinity, and that will tell us all of our possible closed loop poles, and that's the root locus diagram. So as we adjust K from 0 to infinity, that's now sketching this locus of points in the z-plane that map out where our closed loop poles might live. That's proportional control. Let's look now at PI control. Again, proportional was just a controller that was a gain. Now we want to introduce one more component part or a parallel piece to that controller structure. We have the proportional piece, which is proportional to the air. Now we want to make a piece of that controller proportional to the integral of the air. That's where the I comes from, the integral. In a continuous time setting or in the analog setting, then U is 2 pieces. It's made up of a proportional piece, that's K sub P times E of T, plus an integral piece, which is K sub I times the integral of E of tau, where tau is just my variable of integration. We could put that into the frequency domain by Laplace transforming, and now the Laplace transform of an integral is just 1 over S, so that the transformed equation between the air signal and the input to the plant is now given in blue. U is K sub PE plus K sub I over S times E. That's now the structure of a PI controller. But what we want to do is find out, what does a PI controller look like structurally for a discrete time system, Z domain. And that's these discrete equivalents. Let's just do it for one particular technique. You've already learned min, zero mapping, and you've also learned zero order hold. I'm just going to look at one because that will give us the generic structure I'm interested in. Or I'm going to look at the numerical integration technique that we studied back in February using the forward rule, which is really where we replace S that I've highlighted in yellow with this expression in Z, which is this factor Z minus 1 divided by the sample period capital T. Meaning, this is now the expression that we have for a discrete time system's PI controller in the frequency domain. We now have a proportional piece, and we have a second piece that's consistent with the integral piece that we had in the analog case. Are we comfortable with that very first line? All we're doing is substituting Z minus 1 over T for S to see what falls out in terms of this relationship between the error E and the input U of our system. So that once we find that, that will give us our transfer function of a PI controller. That's the idea. In the second line, all I've done is factored out the common error signal, E of Z, or the Laplace, or the Z transform of the error. And then the third line, I've simply found a common denominator. And now there's the key, one of the key pieces of a PI controller. Where is the pole in this transfer function between E and U located in a PI controller? It's right at the Z equal 1, which is consistent with having a pole at the origin in the continuous time case. So now if somebody says, oh, I have a PI controller in the frequency domain version for the discrete time system, you now know that they're placing a pole at Z equal 1. That's what a PI controller will do. It will automatically place a pole at Z equal 1, and that's going to give us beneficial steady state accuracy behavior. That will force, if we keep the closed loop system stable, if we can stabilize the closed loop system, once we have an integral piece in our controller, we now can integrate the error away when we have constant inputs. Meaning, I put in a 4, I'll lock into that 4 with my output if my closed loop system is stable if I have a PI controller. I'm forcing that behavior by putting that integral into my controller. That's why we may want to move beyond just a proportional controller. We may want to move up into a PI controller or a proportional integral. And it's for that reason. We now are trying to enhance our steady state accuracy specifications or our steady state error behavior. If we do just a little bit more algebra on the numerator, now I'm simply, once I had the common denominator, I now have a term that's linear in Z, and I have some constant terms. And all I'm doing now is combining the constant terms in that bottom line or bottom row expression. And the last, or the next to the last step is I'm going to factor out a common case of P from all of those terms so that I now have a gain case of P scaling some factor. And what I want us to look at is this particular factor. Now, that's just made up of 3 different constants combined in some way. We have a gain case of P, we have a gain case of I, and we have our sample period capital T. We combine those in that way, and that's just going to give us a coefficient or a number, a constant. Or we could say that's just an alpha. Now I'm saying what I've circled in this highlight is what I will just call a constant alpha. So that now if somebody says, oh, you want a proportional integral controller in a discrete time system, this is the structure, the generic structure that you're specifying exists in your controller. You have a pole at z equal 1, that's the z minus 1 factor, and then you have a gain, which is exactly the same gain as our proportional gain, and then you have the freedom to locate a zero. I don't know if you remember, but I've talked about having a zero shaker and a pole shaker. Now we have a zero shaker, and we have the liberty of locating that zero wherever we want in the complex plane, as long as it's real. So we can pick alpha. We now have two parameters in this PI controller that we can adjust. The alpha, the zero location, and the gain case of P. And you can sort of see what we're going to do in a design. We may pick the alpha and then adjust the K to put us on our root locus where we want our closed loop poles to live. That's the idea. We're now getting to the stage where we can start to design controllers. Here are two main properties of the PI controller. One, as I have said, we have an open loop zero, that's that z minus 1 factor in the denominator of our controller's transfer function. So we're forcing an open loop pole at z equal 1. And the purpose of that is to enhance our steady state accuracy, or our ability to track constant inputs with zero error, if we can guarantee that the closed loop system is stable. That's the idea. We want to make sure that the closed loop system is stable, then we will have zero error due to a constant reference input. The other property is that we've introduced a zero and an adjustable gain so that our closed loop system looks like this. Here is our plant, G of Z, and we have a controller, and if I now say a proportional integral controller, then we do have this adjustable gain that I'm calling in this formula K bar times a zero factor, Z minus alpha, and that pole is fixed at Z equal 1. That gives rise to the Z minus 1 factor. That's what we get when somebody says, oh, put in a PI controller. What happened when we put in a P controller? A P controller was just the K bar. PI controller now introduces these two additional factors. A zero factor, so we can locate the alpha wherever we want, and a fixed pole at Z equal 1. That's the structure of our PI controller. But to make that consistent with the way that we've been thinking about moving closed loop poles, we can now slide those two new factors into the forward transfer function that we call G bar. And if we now fix alpha, the bottom is now fixed. That's this Z minus 1 factor. And now we have the ability to manipulate K bar to give us our closed loop poles. If somebody gives us a plant G and they say, control this with a PI controller, you can now augment G with a Z minus alpha factor and a Z minus 1 pole factor, and now adjust K bar to hopefully stabilize or give you the desired behavior you want in your closed loop system. And now we can do the same processing that we've done before. Now we can compute the closed loop transfer function. Again, that's our cheer, CG over 1 plus CG. But now C is different. C, I'm going to slide the two factors, the zero factor and the pole factor, in and create a G bar, so that now I have a K bar, G bar over 1 plus K bar, G bar. But the analysis really hasn't changed. I'm still looking at the denominator, which is governing my closed loop dynamics. And what happens in the denominator? I can manipulate those closed loop poles by the choice of K bar, or by moving K bar from 0 up to infinity. That maps out all of my red lines on the Z-plane, and those red lines show where my closed loop poles live. And that's what the root locus is. Those are the values of Z. Those are the red lines. Those are the values of Z that satisfy this characteristic equation, 1 plus K bar G bar equaling 0. And the values of Z that cause that to happen are the closed loop poles, and we'll show those with our red line. Or if we now label G bar of Z as having a numerator factor and a denominator factor, the numerator factor being N and the denominator factor being D, then the 1 plus K bar, G bar, simply once we put that over a common denominator, becomes D plus K bar N. And we're interested in the numerator of that. Or the values of Z that cause D plus K bar N to equal 0, those are our closed loop poles. And if you want the standard form, the standard root locus form, you can obtain that by dividing this last equation, all of your terms, by D, and you're back to this 1 plus K bar G bar equaling 0. And those are your closed loop poles. Which means that we want to be able to sketch the root locus associated with, or the values of Z that map 1 plus K bar G bar to 0, or force that to equal 0. And as a reminder, here are those root locus rules. What's rule 1? Does everybody have that down? If somebody gives you a G bar, what's that going to, how can you find rule 1, or how do you generate rule 1? From G bar. What do you have from G bar? Poles and zeros. You have N of Z and D of Z. So now you can just put the zeros down as open circles and the poles down as X's. Now you have 1 point out of 50 on your exam, right? You have rule 1. Rule 1 is just placing down those open loop poles and open loop zeros as X's and O's. That's all rule 1 is. Rule 2 identifies which real axis line segment belongs to the root locus. And this is where we're cutting up our infinitely long piece of bread. If we have poles and zeros on the real line, we can think of cutting the bread at each of those poles and zero, at each value of the pole and 0. And now what are we doing? We go to each of those line segments and we look to the right and we say, do I see an odd number of poles and zeros to the right of where I'm standing? If so, then that segment, real axis segment, is a piece of the root locus. That's rule number 2, and that's pretty quick to do. Now you're up to 3 points out of 50 on your exam. You've done rule 1 and rule 2. Questions on those rules? You should be able to just do those in your sleep. Rule 3 now looks for breakaway and reentry points. And you may or may not have either of these, depending on the pattern of poles and zeros that you're playing with or that exist in your closed loop or in your system. But now the breakaway points are where you have a relative maximum. The breakaway would be if you had something like this. If you just had two poles, we know that this segment, there's three real axis segments, and only one of those belongs to the root locus. And we have two branches of our root locus between those two poles. If we have two branches, they're coming together. If we simply have two poles, then where do they meet? Where are they going to break away? Right at the middle, halfway between those two poles. That's easy. That's an easy break. If we now had an additional singularity, a zero, now we have this classical structure that I keep surfacing. We have two real poles to the right of one zero, real zero. Do we have any more real axis segments? Yes, now I've introduced another one. Now we have four real axis segments. And do any of those additional ones belong to the root locus? If I now go off to, let's say, minus infinity, how many poles and zeros are to my right? 3, which is odd. So I know that I have this segment on the root locus. I had a breakaway here, but now that breakaway is no longer at the midpoint. It's at the geometric mean, and we'll talk more about that maybe in a minute. But if I don't, there are some additional lectures or material that I recorded this past weekend that talk about that. Not too many have watched it, a third of the class, maybe more than a third. But if you're in that third, thank you for watching that. But now we have a reentry. This is now a circle where the center of that circle is, and that's a terrible circle because this distance is the radius, and this distance is exactly the same radius. So you can see that my circle is not very well drawn, but you can draw a better circle. But the radius is from the zero to the breakaway point, and it's also then from the zero to the reentry point. This is where I would be calling the breakaway, and this would be what I would be calling the reentry. And the reentry point is the same distance, the radial distance from the center of the circle, the zero, to this leftmost reentry point. And Z sub r is now my reentry. How this relates to stability will be impacted by where the unit circle is relative to those poles and zeros. And there may not be a gain K that would produce a closed loop stable system. It just depends on how these poles and zeros are oriented or laid out relative to the unit circle. Those are now our rules. Let's go into an example. Here's example number 3. Hopefully we've been playing along with the right example numbers. My plant now is just 1 over Z. It's a very basic plant. I have a plant that's 1 over Z, and I want to control this with a proportional controller. And I want you now to find the range of K for closed loop stability. This is what you'll have to do on the exam. You should be able to do this. Can you now find values of K that might cause this to be stable? And if it's not, then you draw your root locus and you say, look, there's no value or range of K that will produce closed loop poles that are all inside the unit circle for any given value of K. But you might be able to. And hint, hint, this one you can't. But what is, can you now find that? I'll give you 30 seconds to find the range of K for stability. Where's my stopwatch? You should be able to find that. Oh, we're out of time. What? And k needs to be positive. K is living between 0 and positive infinity. For values of k between 0 and positive infinity, are there any values of k that cause this system, closed loop, to be stable? If you're now searching for points for partial credit, what would you do? First thing you might say, well, what's the closed loop transfer function? And that's our cheer. That's kg over 1 plus kg. And we know what g is. G is just 1 over z. And the denominator is what governs stability. So we're saying 1 plus k g of z, which is 1 over z, equaling 0. Or we now have z plus k over z is equal to 0. Can I find any values, positive values of k, such that z plus k, the roots of that, are inside the unit circle? That's all I'm asking. If I put k equal to 0, is the value of z that satisfies that numerator equaling 0, is that inside the unit circle? If I put k equal to 0 in this formula in the numerator, now I have z is equal to 0. Is that inside the unit circle? Z equal to 0? So we're starting with a pole at the origin. In the open loop, it's stable, correct? With k equal to 0, it's stable. It's right at the origin in the z-plane. That's inside the unit circle. So we're trying to select k to keep the roots of z plus k inside the unit circle. And we can see that k equal to 0 is true in terms of z does live inside the unit circle. Or we could say 1 plus kg bar is equal to 0, and now we have kg equaling minus 1, or 1 at an angle of minus 180. And we have our two rules, or two conditions. We have the magnitude condition. If the magnitude, or if kg is equal to 1 at an angle of minus 180, it has to have a magnitude of 1. And that kg has to have a phase of minus 180. So now we can actually find an expression for k as a function of z. And we can plug in different values of z to find the k's consistent with those values of z. From our magnitude condition, we see that k is just going to be the magnitude of z. Here's our system. There's g bar of z, or g of z. Just an open loop pole at the origin. What's the root locus look like? How many real line segments do we have? We have 2 real line segments. Do either of those, we have one between the origin and plus infinity, and one between 0 and minus infinity, because we have just one singularity, one pole. Is the half of the real line between 0 and plus infinity on the root locus? If I'm standing at 1, do I see any poles and zeros to my right? No. What if I'm standing at minus 1? Do I see any poles and zeros to my right? Yes. Do I see even or odd numbers? Odd. So I can sketch my root locus. And what's the root locus tell me? That tells me all the potential closed loop poles as I adjust k from 0 to infinity. Where do I want my values of z to live if I want closed loop stability? Yes. There's two real line segments because I have split the real line with that that pole at the origin. Now both of those, I'm just cutting my infinitely long piece of bread, and I'm cutting it everywhere I have a pole or a 0. So I've now cut my real line right there. And I'm saying which of these segments belong to the root locus? The positive half or the negative half in this case. But now that I've done that, now I've sketched my root locus, what's the next question I want to ask? I want to know what value of k will produce a stable closed loop system. I know k equal to 0 does. What's my next? I want to find, is there a maximum? Can k go all the way to infinity and I can still be stable? Do you see where I'm trying to direct you? You should be seeing a unit circle. You want your root locus to simultaneously, all branches to be inside that unit circle simultaneously for values of k to give you closed loop stability. How many closed loop poles do you have in this case? 1. Right? We have one pole, one closed loop pole. We want to know, can we keep that pole inside the unit circle? And if we can, what values of gain will we need for that to happen? And we've just found our formula for k. Do you see how we could now find the maximum gain value for stability for this case? We could evaluate that expression for at z equal to -1, and that's going to give us the maximum gain before, if we crank up k beyond that, we'll zip outside the unit circle. So we evaluate k at that boundary, the unit circle boundary, which is z equal to -1. Our formula for the magnitude of k was just the magnitude of z for this simple system. We plug in -1 and find its magnitude, we get 1. Yes, so the question was, what's the meaning of that arrow on the red line? And the meaning of the arrow on the red line is in the direction of increasing k. So now view that as adjusting k from 0 to positive infinity, and that's the direction of movement of my closed loop poles. And as long as I keep my gain k less than 1, I'm going to stay or be living inside the unit circle. Yes? So why did we not evaluate the expression for k at z equal to 1? I think that was the question. Why did we not evaluate k, the magnitude expression for k, at z equal to 1? We could evaluate it and we would get what? A value of 1. But that has no meaning because does the red line ever touch or is it ever located at z equal to 1? No. So we do not have the potential of having a closed loop pole at z equal to 1. What's the lower bound on k in this case? 0. We wouldn't have to even inject or have a magnitude for k in order for our pole, which started at the origin, to stay at the origin. So in this particular case, for a stable system, k lives between 0 and 1. We crank it up more than 1, and we zip outside the unit circle. Pardon? The lower limit really is we put in a value of Actually, we wanted to start at the open loop pole. The open loop pole is going to be stable, so that's with k equal to 0. We didn't even have to plug in any value of z for that. But if you do plug in z equal to 0, you have k equal to 0, but that's because the pole was at the origin. That's why that's the case. Well, you'll find that if you now plug in a pole value based on the expression for k, that's always going to evaluate to 0 for your gain. If you plug in an open loop pole value, because all of those factors are in the numerator of the k expression, you'll get k equal to 0 at your poles, at your open loop poles. So let's just pick one. Let's pick, this might be something that you have to do on the exam. I might say find a k that stabilizes the system. You've now found the entire range of stability for k. It's between 0 and 1. So you could pick any value between 0 and 1 and have and produce a closed loop stable system. Is that clear? And if I just said stabilize the system, I could have 100 different correct answers. They would just have to be k's between 0 and 1. What if we pick k equal to 1/2? Is the system stable? Why is it stable? So now you're looking at the poles of your closed loop transfer function, t sub c of z, and you're looking at the denominator. How many poles do you have? What's the order of your denominator polynomial? 1, it's first order, so you only have one closed loop pole. And we solve z plus 1/2 equal to 0. You now know where that pole is. You have a pole at z equal to minus 1/2. What's the transient behavior? If I walked up and just kicked that system that's now closed loop, I have a gain of 1/2. How will that behave? What's the natural response if I just put an initial condition on that system? How will it move? I see phones out, so I'm not going to move. You're going to have to be a little less subtle. Well, my boss has done that before too. He's filmed me when I've been entertaining. It's embarrassing. But he started laughing so hard that it was not legible. So he was actually shaking so much it didn't matter. So it was fine. I don't know what I was doing, but obviously it was funny. I better not repeat that. So now, what's the natural, or what's the transient look like? Where's your pole? Where's your closed loop pole? Negative 1/2. So now if you wanted to look at that, wouldn't it be looking something like that? An initial condition response would be alpha minus 1/2 to the n. What's happening? It is collapsing, it's stable, but at every sample period, it's going positive, negative, positive, negative, positive, negative, right? So it may be a kind of an erratic transient. You may not be happy with the transient, but it is stable. It's just going to be hopping back and forth. It is shrinking. It's collapsing at a rate of 1/2. That's the common factor between each sample, is this scaling of 1/2. So the transient may be ugly. Yes. Right. So now the question was, if this is first order, I have a real pole. If I have a real pole, what do you know about percent overshoot, peak time, and settling time? Do all three of those exist? Do you have a percent overshoot for a real pole? No, this is just an exponential decay. It's going back and forth, but you don't have an overshoot, do you? It's just an exponential decay. You don't have a peak either. It's not overshooting, so you don't have a peak time. If you have a real pole that's dominating your response, this is dominating the response, it's the only pole there, you just have a settling time that you can calculate. Your percent overshoot would be 0, and your peak time would be 0. Is that? The transient is oscillating. It's going from positive to negative. It's shrinking every time by a factor of 1/2. So if alpha was 10, in the first iteration, you would be at -5. You'd start at 10, then you'd be at -5. Then you'd be at 2.5. Then you'd be at -1.25. So you're flip-flopping back and forth, but you are shrinking. So it is stable. Question? This R value right here is coming from z plus 1/2 equaling 0. That's the R. So the R is equal to 1/2. If you had many different, or if you had a higher order denominator, a third order denominator, you might have 3 real poles. Which of those poles would you use if they're all inside the unit circle to determine your dominant behavior? What did we agree to do in this class? You want the one that's the slowest. That's going to dominate your response. What's the DC gain of our system? With k equal to 1/2, now I'm calculating the DC gain for k equal to 1/2. Our transfer function, closed loop transfer function, hasn't changed. It's still 1/2 over z plus 1/2, but the DC gain we find by evaluating that at z equal to 1. Plugging in z equal to 1 gives us 1/2 over 1 plus 1/2, or 1/3 is our DC gain. That just means if I put in a constant of 6, the output is going to be 1/3 of 6. It will be at 2. If I put in a 1 in the reference input, after all this transient goes away and it's bouncing around, it will settle at 1 times 1/3, or 1/3. So if I was looking at the steady state error for this choice of gain k, I've stabilized my system. My steady state accuracy, or my steady state error, is what my reference is, and I'm saying let's just pick it to be a unit step. My DC gain was 1/3, so my sinusoidal, or my steady state output, that's SS, my steady state output is 1/3 times 1, or 1/3. I take 1 minus 1/3, and I get 2/3 for my steady state error. I wanted to go to 1, I went to 1/3. My error is now 2/3. Is that acceptable? That's going to depend on your particular system, or what you're trying to do with this system. You may not want to have, I specified 1 and you just made it to 1/3. Are you kidding? I don't like that. Is that acceptable? Maybe not. If it's not, if we want to improve the behavior of this system, the way it's behaving in the steady state, what do we now know based on the first part of tonight's lecture? We want to ask Vanna to buy a vowel, right? We want to buy an I. We had a P. Oh, come on. Wheel of Fortune? You don't watch Wheel of Fortune? Pardon? We're still alive? Oh, I guess we are. So now we've bought an I. What do we have? We had a P. I give you an I. You now have a PI. Right? So now if that was ever there, you'd say, oh, pi. No, it's a PI controller. That's what we want to investigate now. So we're looking at introducing a PI controller so that we can enhance our steady state accuracy. What's the PI controller going to do? If we can stabilize the system, the closed loop system, by introducing an integrator term in our controller, what did we just say earlier in today's class that that PI controller would buy us? So that's going to put a pole at z equal to 1 in terms of steady state accuracy. If I now inject 1 into the system, what's the output going to be? If I apply a reference input of 1, what's going to be at the output if I can stabilize the closed loop system with a PI controller? I'm not giving any hints at all. But I put in a 1, and what's going to come out? We're going to get a 1 out. If I put in a 6, if I have a closed loop system that's stable, what's going to pop out at the output? 6. I don't know. They're showing me signals, and those are the only ones I can repeat, those hand signals. So now let's look at what a PI controller does for this system. I'm going to keep the same system. G of z is still 1 over z. But if somebody says, oh, I want a PI controller, that now immediately tells us what the structure is. It's a gain k. It's a 0 factor where I can now locate that 0 wherever I want, and you want to do it wisely. But I'm fixing a pole at z equal to 1. That's a consequence of the PI controller. And you know the drill. What are we going to do? We're going to slide that z minus alpha over and the z minus 1 over, and we're going to create a G bar. And now we're good to go. We know how to sketch a root locus, and we can say, oh, how do I adjust k to put all of my poles inside the unit circle simultaneously? How many poles do I now have? 2. I've actually introduced an additional pole, haven't I? I now have 2 open loop poles, so I'm going to have 2 closed loop poles. And where are the 2 poles starting? By where are they starting? I'm saying at k equals 0, where are my open loop poles? One's at the origin still. That was my plant. And my PI controller gives me a pole at z equal to 1. So let's see what that buys us. Again, you're looking for partial credit. So you immediately say, oh, T sub c, what's my closed loop transfer function? With this collection of pole factors and 0 factors. It's CG over 1 plus CG. What governs the closed loop dynamics? The denominator of that closed loop transfer function. And I now have this equation to play with. My G bar is now a factor z minus alpha in the numerator and a factor z over z minus 1 downstairs. What do we want alpha to be? Now we have our alpha shaker. Where do we shake that alpha? Where do we put it in the complex plane? It's going to be on the real line. Where do we locate it? I've heard 0. I've heard 1. Is Vanna going to bid anything? I. She wants that pi, doesn't she? The PI controller. Well, if we don't know, why don't we just experiment? Why don't we draw some root loci, since you're an expert at drawing root loci? I think I heard one person say, why don't we let alpha equal 0? What happens with that? Well, now I'm going to, what color do you want my controller poles or 0 to be? Oh no, I shouldn't have asked. Let me make it green. I should know better. I have 4 colors I want to select from. Let me put my 0 there. That's what alpha equal to 0 does. What's my root locus look like now for this combination of poles and zeros? Can you immediately sketch your root locus? Is any part of your root locus to the right of z equal 1? If I was standing there and I look to the right, don't I see an odd number of poles and zeros? So that's going to be on there. And that pole and 0 are actually canceling each other out, so they're virtually not there. So if I'm standing here, I could either see 1 or 3. It's odd. So that arrow is showing what happens as I increase the gain k from 0 to infinity. Are there any values of k that will put those closed loop poles inside the unit circle? How many closed loop poles do I have? And this one kind of has 2 answers if you wanted to think about it. You fixed one at the origin by canceling it. And you have another one due to your PI controller's pole at z equal 1. You have 2 closed loop poles. One is stuck at 0. The other one can move from 1 all the way to minus infinity as I adjust k from 0 to infinity. Is that clear? And where do you want? You're now looking at the location of these red branches relative to the unit circle that's trying to be that yellow highlight. Which means I could actually crank up the gain k to put me to that location. Do you see what the gain formula would be in this case? My gain formula is, I'm looking at k, z minus alpha. That was a pole, wasn't it? Whew. I hope this doesn't damage too much, but there's alpha over z minus 1, and that's equal to 1. So if I now solve that for k, I now have that formula for my magnitude of k. And I can plug in different values of z. I've actually set alpha equal to 0, so those 2 z's at the origin cancel in this example, in this case, and I just have k equal to the magnitude of z minus 1. So that now, if I looked at that, k is equal to the magnitude of z minus 1. What would I evaluate z at to determine the bounds of stability in this case? Is there a maximum value of k that I need to stay less than? And where do I find that, or how do I find that k? I want to keep the red branch or the closed loop poles inside the unit circle. I do have a red branch inside the unit circle. As long as I stay with z such that the magnitude of k is determined by the value of z at minus 1, I now am looking at that for stability. Are we good with that? So that's an okay choice for alpha. And I might try to locate a closed loop pole maybe somewhere there. I might not want it dancing back and forth. I may want it to collapse exponentially without a sign change. So I might put it between 0 and 1. What are some other choices for alpha? What if I made alpha equal to -1? What does that do for me? Now I'm locating a 0 there. Again, I'm trying to think, where do I want to put my 0 because I'm now introducing a PI controller? Yes. What? Alpha equal to 0, what makes that okay? So we are looking to make sure that a choice of alpha is such that we now have some possibility of having a closed loop stable system. And with that choice of alpha, we have a fair amount of choice or flexibility. We can pick k anywhere between 0 and 2, and we may not want to put it much bigger than 1. We may not want it to be on the real axis between 0 and -1. We may want to keep k, let's say, evaluate that at 1/2 so that k is equal to 1/2, and that might be a better choice. Is that clear? For that choice of alpha. But now we're just experimenting with different choices of alpha. Is this choice of alpha going to be okay? Can you now sketch rather quickly the root locus for this configuration of poles and zeros? We now have two poles, real poles, to the right of a real 0. It should be pretty quick to find the real line segments that belong to the root locus. We just are looking for an odd number of poles and zeros to the right. What's going to happen now? Well, this pole is going there, this pole is going there, and where do they break away? At the geometric mean, where that geometric mean is relative to the 0, the circle, the center of our circle, and those pole locations. In this case, we have a distance from the 0 to our first pole. If we called this L1, and we have L2 there. And the geometric mean is the radius away from the center, where the geometric mean for this particular pattern of poles and zeros would be the square root of L1 and L2. And in this case, our L1s and L2s are pretty clean. L1 is 1, that's P1, 0 minus 1. So we now have 1 times 2, or the square root of 2. So that our geometric mean determines our radius away from the center. And now I'm getting too many, so that now the square root of 2 is my radius of my circle. Or I'm now at 0.414. And that now is again going to be a sloppy circle. But where is this point? That's a radius away from -1. This should be minus 2.414. What am I hoping is happening in this particular case? What do I hope to have happen in this choice for alpha? Again, I'm interested in, wow. If these were fruits, that would be a terrible looking red delicious apple, wouldn't it? It looks fine? No, it's not so fine, but that's the unit circle. do I have any hope of stabilizing this system with this choice of alpha? Are there any values of k that allow, how many branches of the root locus do I have? How many closed loop poles do I have? How many x's do I start with? 2. So I have 2 closed loop poles. I have 2 branches. I need both of those branches to be simultaneously inside the unit circle for different values of k. Is that going to happen? At k equal to 0, I have a pole at 0 and a pole at 1. So yes, I'm starting okay. And as I crank up the gain k, what's happening? This guy goes here, and this guy goes there. They don't go at the same rate because at some value of k, they are going to intersect or break away at 0.414. And that's not equal distance between 0 and 1, is it not? So one has to cover 0.6 and the other one has to cover 0.4 as k varies. But then they will meet and separate, and then they will become complex conjugate pole pairs. So I can keep cranking k up, and this complex pole pair will continue to move inside the unit circle until I reach that diamond point. And that diamond point I could calculate, I could find the value of k to get me to that diamond point, and that would be my maximum value of k for stability. My lower limit is 0. So I now can have k between 0 and, let me say, k diamond. And what's the value of my closed loop poles at diamond, or the magnitude of my closed loop poles at the diamond? 1. They're on the unit circle. So they are now having a magnitude of 1, and you can use that to help find your k if you wanted to. So that's another choice for alpha. What would be a third choice for alpha? What if I made alpha equal to 1/2? I'm just trying to experiment to show you that with a PI controller, I can have a lot of different possible solutions with a PI controller and still have the same steady state accuracy. In each of these cases, as long as I stay stable, my steady state accuracy will be 0 due to a constant input. My transient may be different. If I go back to the case where alpha is equal to -1, what's the transient going to look like at the triangles? If I crank up the k to get me to the triangles, what's my transient behavior going to do? Will I have a percent overshoot with the triangles? No, they're real, aren't they? So now I simply have a settling time, and I'll keep talking and hopefully somehow change out. But I think I'm being recorded, I hope, still with my other mic, but it sounds weird for you in the classroom, but it's hopefully a better recording. Now you should still hear me in class, I hope. All right, so there's a battery to get rid of. But now if I have closed loop poles at the triangle, I have settling time spec only. Percent overshoot, 0. Peak time, 0, or peak, I have 0 peak. What about at the squares? Now I do have percent overshoot. I do have a peak time because they're complex roots. And that's because I cranked up my gain k a little bit more to get me to the square. And that's why you're going to be paid the big bucks, is because you're going to know how to tweak that gain and how to pick the alpha. So let's look at another possibility for alpha. What if alpha is equal to 1/2? Now I was saying, okay, let me put my controller parameters. Actually, if that was the case, that pole at 1 should be green, shouldn't it? That's my PI pole, or my pole from my PI controller. But what's the root locus pattern look like for this combination of poles and zeros? Whoops. Uh-oh. Do I have any choice or any hope of stabilizing the closed loop system? How many branches do I have? How many closed loop poles do I have? 2. So I want both of those poles, both branches, to be inside the unit circle simultaneously. One pole is locked between 1/2 and 1 for all values of k. The other pole that starts at the origin will zip outside the unit circle if I crank up the gain k enough to push me beyond -1. But this is still an okay choice for alpha. It may not be the best choice, but let's just go with it. Let's let alpha equal to 1/2 for this example. Yes. So now the question was, if I crank up the gain k enough to get me to that 0 at 1/2, what's my gain k? What's the gain required to get me to z equal to 1/2 for that pole between 1/2 and 1? Infinite. I've now cranked up my gain k to infinity. What happens to the pole at the origin? Oh, brother. It's gone off to -infinity, so I'm way past this being closed loop stable. So I would want to make sure that I crank up my gain k only as far as that pole at the origin gets cranked up to a value that keeps me less than -1. So let's look at what we can find here for the range of k for stability. Here's my magnitude condition. I have alpha equal to 1/2. So I have this z minus 1/2 factor upstairs. It's not a z because my alpha is 1/2. So I solve for k, and this is my formula for k. Where do I evaluate that k, or that expression? Is it stable at k equal to 0? Yes, I had a pole at the origin and at 1. So it's stable when k is equal to 0. My upper limit, how do I find my upper limit for stability? For this choice of alpha, this is now 1/2. I now need to evaluate this k at z equal to -1. That's the value of k that will be the maximum I can crank and still remain closed loop stable. And in so doing, I now plug in z equal to -1 and take the magnitude of each of those factors, and I end up with 2 over 3/2, or I now have 4/3 for k. With a PI controller with alpha equal to 1/2, I can now crank up my gain from 0 up to 1 1/3. I probably don't want to make it that high because that's going to get my second pole very close to -1, which probably isn't a very good location. Can I find the steady state error? What's one quick way? You're running out of time on the exam. You've got a PI controller. Are you assured that this system is stable? You could say, oh, pick k equal to what value for stabilizing the system? I would probably pick something bigger than 0 because 0 would put one of my poles at 1. So I now want to put it a little bit. Maybe I say k equal 1/4. I say k equal 1/4, and now I want to find my steady state error. Well, do you really have to find it? 1/4 will stabilize the closed loop system. What's the PI controller do for us stability-wise? I'm sorry, steady state accuracy-wise. It gives us 0 to a constant input. So what's my steady state error if I pick k equal to 1/4? 0, because of the structure of the PI controller. We can verify that. What if we calculate it? The error is r minus y, and y is simply the closed loop transfer function times r. And what's my closed loop transfer function? Well, if I factor out the r, my closed loop transfer function is k times the 0 factor, which was z minus alpha, and I picked alpha equal to 1/2, over the denominator of my open loop system, which was z times z minus 1 plus k times z minus 1/4. The final value theorem I can apply. I don't need to do this, but I'm just verifying that in fact we better get 0 error due to a constant input. The steady state error is now the limit as n goes to infinity of E of n. And that's now by the final value theorem. That's what this is. That's equal to the limit as z goes to 1 of z minus 1 times E of z. Whoops. Oh, yeah, that's right. And E of z is this mess. What's r of z if r is a unit or is a constant? What's the z transform of a constant? I don't know. I'm going to look it up in my table. So you look it up in your table, and you get a over, or az over z minus 1. That's the z transform of a constant a. And I can now plug that into my expression for r. Again, not that I need to, but look what falls out. I've now put all of that E of z expression over a common denominator, and I have two pieces that cancel out or sum to 0. And the z minus 1 factor preceding the big bracket cancels the z minus 1 in my constant input. I now want z to go to 1. Is my denominator well behaved? If I let z go to 1, is my denominator vanishing? No, it's well behaved. What's happening to my numerator? It now does become 0, doesn't it? Because I'm now evaluating z minus 1 at z equal to 1. So that z minus 1 factor becomes 0, so I've now convinced myself that in fact the steady state error, as I already knew by design of a PI controller, it better give me 0 error due to a constant input. And it does. The numerator in that expression was forced to equal 0 because of the pole at z equal 1. That was the design. That's what happens when we introduce an integrator piece in our controller. So with a PI controller, we've now guaranteed we have 0 error due to a constant input. And we were able to talk about different values of alpha, different values of 0 location in that PI controller based on your root locus sketching ability. As I anticipated, we are out of time, but the next lecture, which is lecture 6.4, that's already miraculously posted on D2L, talks about controlling this plant with a PI controller. How does this plant differ from the one we just covered in example 3? Where was our plant in example 3? It was 1 over Z. Is this system stable, open loop? No, it's now starting at 2. And now do you see the pattern that you're going to have if you start controlling this? If we now looked at this guy, we have a pole here at 2, and if we control this with a PI controller, what does that do for us? Well, that puts another pole there. Where do we want to put our alpha? Now we want to be smart in our location of alpha so that this circle pattern starts coming inside the unit circle. That's lecture 6.4. And I'll let you enjoy that on your own.